let's start with the first topic in 4.1, solving systems of linear equations. So the first objective here is deciding whether an ordered pair is a solution or not. So let's see the example. Okay, we have an ordered pair, something like 12, 6. And we want to test if this ordered pair is the solution of this set of equations. So we need to test if this is the solution. We can use the number to replace x, y in the both equations. If both equations are true, then we will say this is the solution for this system. So let's try the first equation. Say first equation, 2x minus 3y equals 6. Now we're going to use 12 to replace x, right? And we use 6 to replace y. Then we check the left side. We will get 24 minus 18. So now the left side, we will have 6. Then let's check the right side. 6 is equal to 6. So we will say it's true. Of course, we cannot just stop here because we have another equation, right? We need to test another equation too. We still use 12 to replace x and 6 to replace y, because this is the pair, the ordered pair we have. And the left side 12, right side is also 12. So it's also true for the second equation. Then we will conclude this ordered pair. We will say yes, it is the solution for this system. Okay, so we need to test both equations. If both are true, then we can conclude that. So we can see another example. This time we have this ordered pair, and we have this system, two equations. So let's see, test the first equation. We use -1 to replace x this time, and use 2 to replace y. Then we try to get the left side. Okay, -1 plus 4, so this side is 3. 3 equals 3. Left side equals right side. So for this equation 1, it is true. It's the solution. But we want to test if it's the solution for the system. So we need to check the second equation. We still use -1 to replace x and 2 to replace y. So let's check the left side. 4 times -1, we will get -4, right? And -2 equals 6. Left side, we get -6. In the right side, we get +6. Obviously, it's false. So if one is true, another one is false, what's our conclusion? We will say no. This one, this ordered pair, it is not a solution. Because we want to test both equations. Only two equations are all true. Then we will say it's the solution. If one is true, another one is false, it's still not the solution. Okay, that's the first topic. Let's check the objective B. This time we want to solving by graphing. We want to solve the system. We try to find the solution, but this time we're going to use graph to help us to find the solution. Let's check the example together. So we know in the system, linear equation system, we have two linear equations, right? So each linear equation, we can draw a straight line. We can draw a straight line. Then we can check which point the two lines intersect. Two straight lines intersect at the point. That point is our solution. So what should we do for these two equations? We can find several points for each line, each equation to help us draw the straight line, right? For the first equation, we can list the table just like we used to do. We can use 2 points, 3 points, doesn't matter. Okay, so if we set x is equal to 3, so we will pick some convenient number. If x is equal to 3, then we will have y is equal to 1. Right? If x is 0, then y is also 0. Oh, sorry. I copied wrong. So it's not the case. It's equals 10, not equals 0. So let's check it again. If x is equal to 0, then let's see, this one is not very convenient for me to draw the graph. So let's say if x is equal to 1, then x is equal to -1 will be good. -1, then y is equal to 3. Okay, if x is equal to 2, then y is equal to 4. So we pick these 2 points to help us to draw the first straight line. Let's check the second one. We can also list several points. So if x equals 1, y is equal to 1. If x equal to 0, y is equal to 2. So now we could use several points to help us draw the graph. So first equation we have -1, 3. So -1, 3 will be like this way. And 2, 4. So I have 4 here. 2, 4. We'll write it around here. So maybe we can draw this straight line like this. Okay, we can draw the straight line like this. This is the first line. And we also have 2 points, 1, 1 for the second equation and the 0, 2. So we can connect these 2 points to find this one. And we realize 2 these two straight lines intersect at this point. And if this point, we can find the number here. It's negative 1, 3. So we will get the solution from the graph. We will get this point. This is the point of intersection. This is the point of intersection, right? So next step, we're gonna test if this point, if this ordered pair is the solution for both straight line. So let's go back to the first objective, right? We have the pair now, and we're gonna use it to test. So the first one will be negative plus 3y equal 10. Let's use this number to test. We use negative 1 to replace x and 3 to replace y to test if it's correct or not. Left side we will get 10 and right side we also get 10, so it's true. How about the second one, x plus y equals 2? We still use negative 1 to replace x and the 3 to replace y. Left side we got 2, right side we got 2. So it's true. Again, if both equations are true, then we will conclude this point. We get from the graph negative 1, 3 is the solution of the system. So for this kind of problem, we only need to find several points for each line. So each equation, we use equation, we list a table to find some points, right? We use these points to help us draw the straight line. For the second equation, we do the same thing. We list the table to find the 2 or 3 points to help us to draw the straight line. Then from the graph, we can find the point of intersection. We write down that value. After that, we still need to test if we do it correct or not. After we test, both equations are true, then we conclude this point is the solution of the system. Okay? So this is always use the same procedure. Draw 2 lines, find the intersection point, then check if that one is the answer. So next objective is try to find some special system of linear equations. Special system. Of linear equation. So what kind of situation we will call them special systems? Let's see. We will talk about 2 special cases by checking 2 examples. The first one, if we have this system, so maybe we will change the form, the standard form. So the first equation, we have the standard form. We will change both equation to the slope-intercept form. Okay, first step, we need to get the slope-intercept form. So for the first equation, 2x plus y equals 7. This is called the standard form, right? We need to change it to the slope-intercept form. We will get this one. And for the second equation, we also need to switch it to the slope-intercept form. We will get this. Then we should observe these two slope-intercept forms. We realize, remember, these two linear equations have the same slope. That's why we need to transfer them to the slope-intercept form, because it's easy to find if they have the same slope or not. So for these two equations, we realize they have exactly same slope, but different y-intercept, right? Because here we do not have any number here, so which means we do not have y-intercept here. So we have this conclusion: same slope but different intercept. Remember what's our conclusion? These two straight lines are parallel to each other. Two lines are parallel. If two lines are parallel, so this is one of the special case. This one is the special system. And for this kind of parallel lines, no intersection point, right? Because they are parallel to each other. No intersection point. So our conclusion is no solution. So this is one of the special case. Two straight lines are parallel to each other. Then they will never have the intersection point. If they do not have intersection point, then there's no solution for this system. So please remember, this is the first special case. Let's check another example, talk about another kind of special case. So we can, of course, you can check the slope and the intersect for two equations to get to the conclusion. Of course, you can also use graph to help you to draw this kind of two lines. Then you will realize from the graph, you can also get to the conclusion these two lines are parallel to each other. So here, I will just use the slope-intersect form to help us to find these two straight lines are parallel to each other. If you want, of course, you can always use graph to help you. So same here. If we observe these two equations, we will find that these two equations are kind of weird. Because for the first one, we get x minus y equal to 3, right? And the second, we have minus x plus y equals negative 3. So if you observe this equation, especially the second one, if you times the equation both sides by the negative 1. So left side, if we times negative 1 for both sides. Remember, if we multiply by the same number for the both sides of the equation remains the same one, right? So we will get x minus y equals 3. Then we realize it's just the same equation as the first one, right? It's just the same equation. So this case, we call the two equations are identical. They are actually just the same straight line. If we draw the graph, we will find this is the same line. They are just identical to each other. Although they looks different, they actually are the same line. So if they are the same line, these two are same line. They are same line. Then they have infinite solution. All the points on the line will be the solution. So they have infinite number of solutions for this system. Okay, so for this kind of situation, maybe you need to draw the graph to help you figure out they are just the same line. This case, if we draw the graph, then it's easy to find that they are just the same line. But if you can observe to find the relationship just like then you will find if you multiply both sides by -1, you will get the exactly same one. So you still have two ways. If you can find the relationship, transfer one to another one, then you can prove they are just the same line, right? Another way is try to find the several points for each equation, then try to draw the straight line. You will realize these two equations, they are actually the same line. If they are actually the same line, then they have infinite number of solutions. So this is the third objective. Two special case. Remember? Two special case. One, we use slope-intersect form to find if they have same slope, different intercept. Then they are parallel. If they are parallel, they do not have intersection points. So they have no solution, zero solution. Another case is if these two lines have same slope and the same intercept. So we can also try this way. If we switch the first equation to the slope-intercept form, we will get x minus 3. Y is equal to x minus 3. If we do this one, the second one, we will also get the same one. So this is another way to prove they are actually the same line, right? We can also change them to the slope-intercept form. So this kind of problem, it's always helpful to transfer all the equation to the slope-intercept form. Then we compare if they have the same slope but different intercept, they are parallel. So they do not have intersection points. So they have no solution. If we change them to the slope-intercept form, then realize they have same slope and the same intercept, which means they are exactly the same. If they are exactly the same, they are just the same line. If they are just the same line, all the points on this line will be the solution. So they have infinite solution. So the last objective, just try to find the number of the solutions. So this time we do not find the exactly solution for the system. We just want to determine if the system has one solution, zero solution, or infinite solution. Okay? So actually, from previous example, we know we totally have 3 different situations. One called one solution, right? we have a straight line and intersect at one point. So we will say one point of intersection, one solution. One solution. And we have the second case, we will say we have maybe two parallel lines. So no intersection point, so no solution. And the last one is we just have one line. Two equations are actually the same line. So we will say they have infinite solution. So we total have three different situations. Now, objective D, we cannot use the graph to help us this time. This time we will try without graphing to help us determine the number of the solutions for the system. Let's see the example. It's still possible, right? Let's see this example. We could, remember, use the slope-intercept form to help us determine the number of the solution. So let's see, we have this system, and the first step, we're going to change them to the slope-intercept form. So for the first equation, we will get y is equal to half x minus 2. Yeah, half x minus 2. And the second one, we will try to get, it will be y equals, is still half x minus 5 over 2. So we change the different equation to the slope-intercept form. So the slope-intercept form is very helpful to do this kind of question, right? So after we have the slope-intercept form for both equations, then we can observe. We can compare if these two equations have the same slope. Yeah, in this case, they have the same slope. Do they have the same intercept? No. The intercepts are different. So for this case, we will know this is one of the special case. We call it two lines are parallel. If two lines are parallel, so they do not have intersection points, we will say no intersection points, no solution. So we determine the number of the solution for this system is 0, right? No solution, so the number is 0. Let's check another example. So for this time, we still need to transfer it to the slope-intercept form. So let's see, what should we do? The first one, it will be 3x minus 4. And the second one, we will get, let me see, negative half x plus 4. So you need to do lots of practice to make sure you can transfer the equation to slope-intercept form very quickly, just like I did, right? Okay, so after that, we can compare the slope for these two equations. And we know the slope for the first equation is 3, and the slope for the second equation is negative 1/2. So they are not the same slope. Not same slope. if they do not have the same slope, they will not be the same line, right? Same slope, same intercept, they will be the same line. Same slope, different intercept, they are parallel. So this one is not the parallel special case. It's not the identical special case. So this is the general case. We will have one point, one intersection point. So it's just one solution, right? So it's just one solution. So we determine the number of the solution for this system. It's just one solution. For that one, it's 0 solution, right? Of course, if we find the two equations are exactly the same slope and same intercepts, then our conclusion will be the number of the solutions is infinite. So we total have 3 possible conclusions, 3 possible answer, right? 1, 0, and infinite. Again, if they have different slope, we will have one solution. If they have same slope, but their intercepts are not the same. So same slope, different intercept. This will be the case. They are parallel lines. They have no solutions. So the number of solutions 0. Another case is if we switch all the equations to the slope-intercept form, and they are exactly the same one, then we will say they have infinite solutions because they are the same line. All the points on this line will be the solutions. So they have infinite solutions. And if they have solution, one solution or infinite solution, we will say it's consistent system. So if it has solution, no matter one solution or infinite solution, then we will say consistent system. Consistent. This one is also called consistent because it has solution. It can be one solution or infinite solution. But if it has no solution, we will say it's inconsistent. Okay? This is just the definition. All right? So yes, has solution, then it's called a consistent. No solution, it's inconsistent. So that's for 4.1.